let's start talking about Iceland and about fractures and folds that you can find during field activity in Iceland. In this photo, you can that is has been taken from one of my students working in the field. You can see what is very normal in Iceland. So very recent lava flow, volcanoes, giant folds, and then very recent fractures in the ground. Here there is the person for scaling, and along this fracture we take a lot of measurements to understand how these fractures open and how they can move over time. This fracture probably occurred after the recent most lava flows that is as old as around 2,000 years. Talking about Iceland, it is defined as land of fire and ice. Why? Because in Iceland there are a lot of eruptions that occur over time. For example, it is the visual eruption from Bonali, very recent. Here there is the Tiga Valley National Park, that is an area that we are going to see where North America and the Eurasian plate move with respect to each other. But it's also a land of geothermal activity, as well as the Vatican place is the largest place in Europe. This is a typical fold that you can find in Iceland, and they are as high as around 20, 30, 50 meters. Why? Iceland is located in the mid-Atlantic Ocean, along the mid-Atlantic region, at the very north of Europe, so near the Circle Pole. So that's why it's a land of ice. But why it is a land of fire? Look this video where it is explained how during plate separation there is a heat that rises from that. So mountain rock migrates upwards, and small pods of magma can reach the surface. In this case, new crust is created. It's how new crust born on our planet. But magma can reach the surface, giving eruption on the seafloor, and when eruptions are a lot, the seafloor can grow above the sea level, like Iceland did. In this case, the two plates split apart each other, more or less around on the Earth between 3 and 10 centimeters per year. Iceland is splitting apart about 2 centimeters per year, so a bit with a lower spreading rate. In addition, Iceland is located above the North Pole, so there is a huge amount of heat flux from that facilitate the creation of magma and then the creation of new crust. Particular, Iceland is defined as a hot spot, that is a volcanic region to be fed by the lightning mantle that is enormously hot compared with the surrounding mantle. So it's an area with very hot flux from that allow the creation of new magma and new crust. This is why Iceland is above the sea level. This hot plume is working more or less for the latest 60 million of years. And you can find traces from Greenland to Scotland about this. This is like the trajectory of opening of Iceland, so for the North American and the Eurasian plate, over the latest 60 million of years. But Iceland is also land of earthquakes. Here you can see the epicenter location of all the earthquakes along the mid-Atlantic region. Do you remember what is the epicenter location of an earthquake? Who can explain this, please? A volunteer. You. Yes, you. initial expression of the earthquake is the location of earthquake on the map, excluding the depth, because the depth is the hypocentral location. But as you can see, they are aligned along the mid-Atlantic ridge, but something is different on the land, on Iceland. This is why, because of the volcanism, because of the hot plumes, there in Iceland forms a small number of microplates that move each other, so the deformation that occurs on Iceland is slightly different of what occurs along the mid-ocean ridge. For example, here you can see this cluster, this alignment of earthquakes, and this is defined as a seismic zone. And in this case, in this area, these two plates move each other, different from the mid-Atlantic ridge. In this image, also you can also see the main volcanic zone in Iceland, that is the western one, the eastern one, and the northern one. With students, we have been working for the latest 5 years in the northern volcanic zone. It is the most interest because, as you can see here, there are two other areas where we have a lot of earthquakes aligned along a main preferential direction. The northern one, the northern volcanic zone, is very interesting because it is formed by 5 different rift zones. Each of these zones is separating, is splitting apart. The overall area describes the superficial expression of the mid-Atlantic ridge. But, much more important, as you can see here, there is this very nice alignment of earthquakes, like also to the north. This whole area is described as the tectonic fracture zone. It's one of the best places that you can see in the world because there is a transfer fault that reaches the surface. Transfer fault is a fault that crosses the mid-ocean ridge. Usually it is 3,000, 4,000 meters below the sea level. In this case, it reaches the surface in this segment and then continues below the sea level. Much more important for seismic hazard, this fault generated earthquakes larger than magnitude 6 in historical time, during historical time, inducing damages and small tsunami along the coast. So the area is subjected to seismic hazard, but is also subjected to volcanic hazard because there are two main centers, the tectonic volcano and the Krater volcano, that both give eruption during the latest 2,000 years. But now we see some video by fieldwork of this year, of this summer. This is an example of typical fracture that you can find in the ground in Iceland. That's me and the student. They are deeper and deeper, sometimes you cannot see the end of the fracture, and sometimes they are as large as 5, 6, 10 meters. So it's impossible to take a field measurement. You need something different. You need a drone to study this kind of structure. This is another example of a normal fault that in this case it was as high as 20 meters. Me and my colleagues for scale also in the video. And these are the typical fractures and faults that you can survey in Iceland. But since sometimes it's a very huge problem to collect data by field activity, drones can help us. In this case, we made a very small survey with a mini drone that we used yesterday. So we collected about 50 photos, then create the model in the lab, and then we take measure in the lab. This is why I think that working with computer paper is very important, because if in case I collect thousands of measurements in the field, I need something to accelerate the process to collect the data. something that automatizes the process. Because this is why I feel that collaboration with people from computer science is much more important to save a lot of time. You will see in this afternoon in the lab how many times take the process to create a model using 100 photos or 50 photos that we can take in the field. Now a very brief introduction about why fractures and folds form in Iceland, and then we go to work all together on Google Earth, looking at some places and try to identify these kind of features on satellite images. Definition of stress. Stress is a force acting on an area, is a pressure. So for example, if I push the head of Eddie, I make a pressure on Eddie. So I induce a stress on Eddie. In case I take a piece of rock and apply the same identical stress on each face, I induce a uniform hydrostatic stress. But if I apply, as it is usually in nature, different kind of stress with different modulo, I induce a differential stress. In structural geology and active tectonics, we define it as maximum stress, the sigma 1. The minimum is sigma 3, and the intermediate is sigma 2. If I took a sample of rock, and then apply a differential stress, sooner or later, a fracture will occur in the center of the rock. It depends on how many stress I apply. And if I continue to apply the stress, sooner or later the two blocks move each other. And so there will be the creation of a fold, like we've seen in the video, 20 meter high. Okay. You know this one, too much complicated. What happens in nature? If I apply a force, the sigma 1 is vertical, sigma 3 is horizontal, suddenly I can also use an earthquake, because when a fold slips, it depends on how it slips. If it slips very slowly, probably I will not have an earthquake, but if there is function, something along the fold that don't allow the movement, there is an accumulation of energy that is released during earthquake with episodic movement of the fold. What happens in Iceland? This can be assumed as the configuration that we have in Iceland, that with the greatest principal stress that is vertical, the latest is horizontal and corresponds to the spreading direction, so the direction of separation between North America and Eurasia, and the intermediate sigma 2, is perpendicular to sigma 3, but it is also horizontal. So what happened in Iceland? In Iceland we have a volcano, we have great separation, so we have the formation, a lot of fractures at surface, but also fractures or discontinuity at depth, and the magma can rise along these fractures. Okay, what we can find in the field? We have extensional fracture that we call joint. Is a surface that separates two blocks or rocks without any movement between each other. If I have small movement, I have a shear fracture with a movement along the surface like a shear in a right or left manner or in vertical manner. Or, as you have seen in the video, we have extensional fracture, so that we call them fissures, where at surface we have separation of the two blocks of rock. Or, finally, we have normal fold, because if I continue to apply the stress, the pressure of the rocks, sooner or later they move and have a creation of a fold, of a vertical offset, as we see in the other video. Okay, avoid the definition. About the magmatic intrusion in Iceland. If I create space, magma can rise, or magma has enough pressure, so has enough energy to rise itself, can create a new fracture, can create the space it needs to reach the surface. But what happens at the surface? When light try to rise the surface, the two blocks of rocks move apart, and then the central block drop down, and I have a creation of two folds that face each other with the creation of a graben. These are photos from the field. These are examples of dike in Iceland, these very light green cuts that you see in the rocks. And this is another example from a colleague from Iceland of a dike that reached the surface and that created an eruption. Okay. This is another video from the northern volcanic zone where there is a small graben, probably induced by a dike below that doesn't reach the surface. Okay, and for scale, this is the road. This graben has a vertical offset of very, very few meters, 2 or 3, it depends on where you take the measure. But if you see this graben, it's very straight, has a preferential direction, and below this direction, below me, there was a volcano. So, dike reached the surface in the past. As you can see, out of the graben, there is the formation of new fracture, because the tectonic reading is always acting on the rock. That is the volcano perfectly aligned with this graben. When someone in this room has been above the volcano, ooh, behind you. Okay. Now,
I don't understand the link between the dike and the gravel here.
okay. This is a skin.
Okay.
When the dike tries to reach the surface, can favor the formation of new normal fall and so the creation of a graben. In this video, I didn't find dike because it was below in the field, but probably this graben was used by a diking event, because in Iceland it's very well known that something is everything is episodic and happens during a rifting event. In a rifting event, you have formation of new faults and fracture, and that like intrusion, and sometimes eruption. So now we have more or less half an hour to work all together on Google Earth and to see other spherical photos from the northern volcanic zone. So what I propose that you work in group, and you have to firstly to identify where the northern volcanic zone is. You have to identify the Useric Flaty fault, that is the transfer fault that you can practically see on Google Earth. That's why you are some geologist, geographer, and computer person. And also you have to identify the different rift zone that you see in the map.
We just identify the transform zone here with this lake in a small graben.
Can you speak?
We identify the transform fault zone here, and in particular with this lake, which is situated in a small graben. So the fault continues here, and you can see all there is 4 or 5 lines, fault lines here, oriented towards the northwest southeast.
Okay.
So here, and so that forms some graben and horst, and I think this is a graben. The lakes can just
Graben
form
or
the gravens.
pull apart maybe?
Huh?
Graben or pull apart maybe?
Ah, yes, maybe pull apart.
I don't understand it goes like that.
Yes, and yes, and it ends, I think, with the Google Earth.
We have overlapping.
Yeah, with Google Earth we cannot see so much, and I think the faults maybe end in this zone, like here.
All of you agree that the fault ends
So this zone.
there or not? Because on the geological maps, the fault seems to continue.
Yeah.
check on the satellite image if it's true or not.
I don't know where am I.
That's good.
Comparing to the geologic map.
Yes. Now,
There is a. It's here.
Three.
Like, I think it's.
Exactly.
They
They usually classify the transform code continuous,
Yes.
reaching the rift zone. And that is the point that Marco showed at the very beginning in the video of the triple junction, where the transform code joins the rift zone. Okay. Another volunteer to identify the tesseract here features wall from another group.
I can choose them.
Then the first table.
Yeah.
Fine. A volunteer, please. You can have in the class to show more or less where the first read zone is. Why you? What's the, yeah, you were the first one. Okay. You have to suggest us where this read zone is. That is the first to the west. That is the tesseract here, Fisher's Sword. Where you can see some faults.
Here.
Yes, okay. That are faults, I agree with you, that are affecting the pre-glacial unit. So all the units, they are very well developed because they've had older units. So the units are subjected to a longer time and a larger time window of deformation. But if you zoom somewhat here, maybe there is something more. Have a look. Zoom in, zoom in. Yes, can you see any fractures, any folds? Because you are looking at the recent lavas, post-glacial units. Okay. Okay. Now these are all these are fractures affecting the recentmost unit, post-glacial units. Okay, so the rift involve pre-glacial and post-glacial units in this area. Can you find something more to the south, along the same rift? Now we are crossing more or less the using platform. Yes. Okay. Stay there, stay there. A bit not. It's to the north.
No. What did you show?
You.
Hey, come on.
No, you.
I didn't show that. You told me. That is the graph.
Okay. more to the south along the same rift, here there are evidences of normal faults from satellite image. And also this affects post-glacial unit. More to the south, there are other fractures affecting again post-glacial unit. But if we move to the west, there are pre-glacial units that are anyway affected by faults again. So the tertiary here, fissure swarm, is characterized by pre-glacial and post-glacial units, both of them affected by faults. By field checks, you can understand which fault is active, which fault is not active, and so on. Okay, thank you. Check the geological map. Okay. This is the recent most unit. So try to find this lava flow and then we were looking over this area. This area. This is going to be an accessory. Yes. There is most. You can see. No? Any suggestion from you? People? Any suggestion? Any other volunteer that can come? You? Oh, good. Yeah, that's
good.
very good. She is very expert with RGB color, so
Yeah.
he can help us. This one. Okay. But first, please identify the recentmost lava flow. That is white in the geological map. It's an historical one. Try to find that lava flow on Google Earth. Yes. This is very, very important to identify the recentmost lava flow. Yes, it's the black one. It's the black one. The black one. And as you can see, can you zoom this area? Okay. There is a very big set of fractures that appear after, northward of this lava flow. Why is this very important? This question is for all of you. Why is very important this area? First one is a panoramic view taken in the field of the area, and you can see back here, those in this zoom, they are implementing a new power plant in the area because there is a lot of heat below the ground because of tide intrusion, because of flux from the ground. So the area is getting more and more important because there is free energy for industry. Free energy. There are a lot of people from Norway that are coming in Iceland because the cost of energy is very low for siderurgy things. Okay. This is the panoramic view. These are the faults. in the area. That is the power plant in the back. And this is why my colleague collects the data in the field. Okay, we are 10 minutes. Okay, in the next 10 minutes, we can talk about techniques to collect data in the field. Okay, this is a brief introduction of the area that we have just seen. Here there is the set of folds that can identify the usage flappy fold. That is a dextral strike slip fold with also a vertical component. This is why there was the creation of this natural barrier for the port. The age of lava is around 14,000 years old. Then there are recent most lavas that are in a way affected by fold and fractures again. And the power plant is more or less here, in this area. In this area there are very recent vents, very recent area of small volcanic eruption or volcanic activity. Okay. In these 10 minutes I show you an area that we survey using drones and why they can be very useful to use. So we work in an area with lava as old as 3,000 and 10,000 years old. Okay, let's skip this one. Okay. These photos are from the graben that you have seen in the videos. The graben is in an area that is 2,400 years old. What we have done in this area? We have done a survey with the drone, but we have also collected classical fish field measurements to have a comparison if the data from drone are reliable or not. And we survey fault scars, also using a laser ranger finder that give you a precision around millimeters. But we also survey fractures. This is an example of a very small fracture where we can take the strike, the direction of the fracture, but also the opening direction that should be related to the spreading direction of overall Iceland. Why we can do this thing? Because lava flow, when cooled, form joints, form columns. And when they separate each other, you have piercing points that you can collect in the field to reconstruct the strain field in the area, the strain direction. We discovered two types of fractures in the area. One with pure extensional fracture, so an opening that is exactly orthogonal to the direction of the fracture, and surprisingly, a lot of fractures with a very huge lateral component. It was unexpected at the beginning of this work, like a strike slip fault. About the survey that we've done in Iceland, we have worked with a giant Phantom 4 with colleagues from another group in the University of Bicocca, and look at this picture to have an idea of the dimension of the structure that you can survey in Iceland. That's for me to scale. What is reported on the geological map is just a line. If you go in the field, you discover that this line is represented by a series of fractures. And sometimes you cannot walk to the other side because they are larger and too much deep to go to the other side. So you need something, right? You need a drone to make a survey from the above to cover the area. And this is exactly what we have done. This is an example from the above, and from the above you can see how much these fractures follow the columnar joint that are below, that characterize this lava flow. So they are not exactly a perfect straight line. Here we remind a bit how the workflow is. So we have made a plan in this example that is the graben. We choose the area to fly, the altitude, that we define the path. Remember, sorry, we didn't have time yesterday to take ground control points to better georeference the area. And then we start with the drone flight. And then in the software, we have the fault alignment, we reconstruct the sparse cloud, then the dense cloud, and then generate the digital elevation model and the optomosaic. We are going to follow this workflow this afternoon. And these are the results. For example, the gradient that you have seen in the video. We have done two different orthomosaics taken from different flight of altitude, 100 meters above the target and 550 meters above. The best one, obviously, was the lower one with a resolution at the ground of 2 centimeters for the orthomosaic, as well as for the digital elevation model. But what is very nice and interesting that on this very detailed digital elevation model, you can run some cross-section and try to get a lot of measurements of the vertical offset that you can compare with data from the field. And you can also quantify along the same fold continuously the vertical offset to understand if this fold has a regular shape, is symmetrical or asymmetric, and so on. This is a comparison, just as an example. These are the data collected in the field that we compare with the data from drone, also from 2 different altitudes. What is important? That the average direction is almost the same. As you can see from the Ross diagram, the data collected with the field with the drone are more or less the same. And this is very important because it seems that you can use drone to collect huge amount of data. In these graphs, we compare again the data between drone survey and field survey, and the difference between the data is always small. It's always in the error that you can do on your own in the field, using the table, using the compass. So we are in the error of that human can do. So why not using drone to huge collection of data? This is another comparison from satellite image and drone image. As you can see, this is the best satellite image that I found from the area. It was around 50 centimeters per pixel. It was impossible to get information about the open interaction, for example. With orthomosaic from drone, both from 1,000 and 500 meters above the target, you can collect on the same area a large number of data. And much more important, looking at the geological object from the above, you can avoid problems that you can have in the field. For example, this is a section of a fracture from the field, and the problem is that the real amount of opening of the fracture was inside the fracture. It was impossible to go in. From the above, I can have a better view of the fracture, looking at the strike, quantify the amount of opening of the fracture, and then the opening direction. And also, I can check if there is something strange regarding the topography. Because, for example, for this fracture, we identified that there was a sort of bulging in the surface. It was quite impossible to catch this thing in the field. This bulging could be related to that intrusion. So to conclude, this was the largest area that we surveyed in this work that is going to be published in a couple of weeks. And over this area, we collected a total amount of, where is the information? 275 data. This was done in, the survey was done in a couple of days of work, considering the weather condition, consider we have, during the first time we have just 3 batteries of the drone. Let me say that to collect the same amount of data, instead of two people that one working with the drone, one is placing the target and collecting the GPS point to reference the model. To collect the same amount of data, it is needed about 5 days for 2 people working in the field. So in this case, we half the time of work in the field, collecting more and more data than field activity. And this is very, very important when you work on a geohazard, to have as much data as you can to have a complete picture of how this hazard works and how can you contribute with new data. Okay, avoid this slide. I would like just to show you this video related to the Vardaburg eruption, because collecting information about the location of the earthquakes that occurred during the dike intrusion, this working group was capable perfectly of tracing the propagation direction of the dike. This to convince you that in Iceland something is episodic, occurred during rifting event, so we have more geohazard, but the two much more important are volcanic hazard and seismic hazard that are related to each other. Okay, we have no time to see the other slide. Okay, that's all. Thank you.